So we can start now. So remember last time we talked about the zero dynamics, and we looked at linear systems and specifically linear single input systems, and we showed that if we take an output of interest, the number of times we need to differentiate this output for the input, the control input to show up, is exactly equal to the relative degree of the transfer function, okay? The number of poles minus the number of zeros. And so, which means we end up with something where we have the variable of interest, which we've differentiated n minus n times. And we can make this stable by control, right? And then we have a leftover dynamics, okay? Nth order. Leftover dynamics. And we saw that this dynamics was simply 1 over the numerator of the transfer function, okay? So remember, maybe I'll just write it again. It was 1 over b0 plus b1s plus bmsm. So it was 1 over the numerator of the transfer function, and therefore this leftover dynamics was stable if and only if the original transfer function had all its zeros in the left half plane, in other words, was minimum phase, okay? And we showed more generally that this, in the case of linear system, it was a kind of a general result. In other words, this idea of picking a variable of interest and differentiating until you find the input and then forgetting about the rest actually in principle works if and only if the system is minimum phase, because basically this leftover dynamics will take care of itself, okay? It will take care of itself with time constants defined by what the zeros are, okay? But it will take care of itself. We said, though, if we want to extend this to nonlinear systems, we can define what's called the zero dynamics, okay? And the zero dynamics is the dynamics that could correspond to maintaining the state exactly at zero, and that's uniquely defined. And we can even say, we will say that our nonlinear system is minimum phase if and only if, by definition, the zero dynamics is asymptotically stable. But of course, since we're dealing with a nonlinear system, the relation between the stability of the zero dynamics and the relation of the stability of the leftover dynamics, okay, is not as simple, okay? In the case of linear system, if the zero dynamics is stable, so is the leftover dynamics. In the nonlinear systems, it's not as simple, so you can define it, but it doesn't immediately imply that things that will work. Okay? And so you have to be more specific about that. We also notice that there was a strong analogy between this and what we had played with before by defining a composite variable, which in turn defined, a sliding surface and things like that. So when we played with composite variables, right, we started with a system whose relative degree was n, okay? So we didn't have this problem of leftover dynamics, okay? We started with x to the n equal, okay? So that wasn't the problem. What we did, though, is we defined the leftover dynamics to be a nice stable dynamics, okay? That was the dynamics of S. So it was kind of the other way around, right? We chose the leftover dynamics to be something nice and stable, and such that the relative degree of S be precisely 1. Okay? So it's the same family of ideas, but used in a different way. Okay? In the case of S, we chose S so that its relative degree be 1, and the corresponding leftover dynamics defined by S be nice and stable. Okay? So it's the same family of ideas, but it's not, of course, the same use. Okay. So then we moved on to what's the central result in all of this, okay, which says if you have a system, so this was 6-3, right? So if you have a system x dot equal f of x plus b of xu, we doing this in the single input case, all of these results extend to the multiple input case. We wondered, when is it the case that we can put it in this very simple form z1 to the n equal u? Okay, so when does there exist a state transformation, smooth invertible state transformation, z equals z of x, such that the corresponding z can be written as one scalar z1 and its derivatives up to order n minus 1. So that gives the basic structure of the state, which in the linear system would correspond to the first n minus 1 equations in the companion form. Okay. And the last equation, z1 to the n equal v. Right? So when can we transform the system so that the state is this, and then more easily such that z1 to the n equal v, where once we have v, we can have u. In other words, in here we wrote that u can be computed back given v using an equation of this form. So that's the question, right? And that's the theorem we're discussing, not proving, just discussing. And is the central theorem of this whole story. Okay? And it's the central theorem of this whole story because it gives a necessary and sufficient condition for this to be true. All right? So, in other words, assuming everything is exactly known, when is it the case that you can do this? So when is it the case, basically, that your system is really a sheep in wolf's clothing, right? Because it's basically equivalent to this. Okay. All right. So for this, we had to define a number of tools, which are commonly used. Okay. So one is what we call the Lie derivative, okay, of a scalar function of the state with respect to a vector field. And we said that these Lie derivatives could be defined recursively. Okay, so we could say that LF0 of h is equal to h, LF1 of h is equal to this, right, LFH, which is gradient of h times f. So the Lie derivatives is the directional derivative, if you want, of h along the direction of the vector f. And we could also define recursively LFIH, which is LF of LFI minus 1h. So basically, based on this notation and the LFIs, you can see that we can keep track formally, right, of recursive differentiation of a given output, okay? And therefore, we'll be able to keep track formally of things like Z1, Z1 dot, and so on. All right. So that was the Lie bracket, the Lie derivative, sorry. So we also define an other operator. Okay, so this operator takes a scalar h of x and a vector field f of x and returns a vector field. Okay, returns a scalar. So you take a scalar h of x, you take a vector field f, and you return the scalar, the dot product, delta h times f. Now we have another operator which we called, well, which is called the Lie bracket. And so this takes two vector fields and returns a vector field. Okay, so this takes a scalar and a vector field, returns a scalar. This takes two vector fields and returns a vector field. Okay, and it's Jacobian g times f minus Jacobian of f times g. And incidentally, since we'll have to play with recursive differentiations, we can extend this idea recursively, okay? So this Lie bracket we can denote as ADFG, okay? If you think of it, I wrote f plus b, or it could be f plus g, right? If you think of it in here, of course, f of x and b of x don't play the same role, okay? So here, f and g more or less play the same role, so if we use a notation like this, we make them look different, right? This is saying, well, f plays this role and g plays a different role here. So this, if you wonder why it's called ADF, the AD stands for adjoint, okay, which again comes from the kind of tools you need in differential geometry. And the idea is that you can similarly do ADFI of G, which will be the Lie bracket of F with ADF I minus 1 of G. Okay. So you can recursively define these Lie brackets, okay, in this, using this notation, okay? So LFI and ADF I, okay, for these recursive Lie brackets. Okay, and the last thing we defined was what we called involutivity, and maybe I won't rewrite it, but involutivity is saying, okay, suppose you take a family of vector fields, F1, F2, Fm, right? So, and you take an independent family of vector fields, meaning that none of these vector fields can be computed by weighted sums of the others, okay, where the weights could depend on the state. So you take a linearly independent set of vector field. This set of vector fields spans a space. Okay, it's all the linear combination, the linear state-dependent combination of the set of vector fields. Okay. Now, the set of vector field is said to be involutive if whenever you take the Lie bracket of any two of these vectors in it, you end up still in the same general spanned field. Okay, you don't get out. Okay, so taking the Lie bracket doesn't let you explore other regions. Okay, you're still within the linear combinations of the original vector fields. Okay, so involutivity says taking the Lie bracket, you're still in the same set. Okay, it's kind of a closure property. Okay, so, and that's related through something called the Frobenius theorem, which is a central theorem in differential geometry, to integrability of certain equations, and we'll come back to this a little. Okay. Any questions so far? These are just definitions. Okay. Okay. So that last definition was involutivity of family vector fields. Okay. So now for the theorem. So let me state the theorem without proving it again. The proof is discussed in the book, but here we will just state it. So this is in the book. It's stated as theorem 6.2, and you have a history of where this theorem comes from in the book as well, with various authors with various contributions. So the theorem is a necessary and sufficient condition for this to be possible. Okay, so in other words, for finding a state transformation so that the transform state has this simple form. And of course, then the last equation is just z to the n equal v. So a necessary and sufficient condition is the following, that the two conditions be verified. So it's 1 and 2. The first condition is that if you take the vector fields B, ADF B, let's just call this G to be consistent with the notation in the book. It doesn't really matter. So if you take G, ADF G, namely the Lie bracket of F and G, ADF square G, ADF n minus 2G, ADF n minus 1G. So if you take this family, how many vector fields do we have? We have n vectors, fields, okay? G, ADF, G, and so on. Okay. So if we take this family, indeed you get an independent set of vector field, okay, linearly independent if we want to be more precise, okay. So in other words, there is no way to compute any of them based on the weighted combinations of the others, okay, where the weights are scalars, possibly state dependent. Okay, so that's the first condition for this to be verified. And the second condition is if you take the same family of vector fields, but you forget the last one, you just take the first n minus 1. So G, ADF G, ADF square G, ADF n minus 1, s minus 2, sorry, G. That family is involutive. We already know, of course, that these vectors are linearly independent because those are, okay? But that family is also involutive. Okay, so that's the theorem, and we're going to explain or try to explain what it means, okay? But that's the story. Okay, so it's basically saying you take G, what the equivalent of B of X, right, if you want, and you take the Lie brackets, the recursive Lie brackets of G with F. Okay? And the first condition is that if you go all the way to n minus 1, so you have n vector fields, they span an n-dimensional space. So they are linearly independent. Right? You have these n vector fields, each of them of dimension n, and you say they are linearly independent, which means they span an n-dimensional space. And the second condition is that you take the same one, but you forget about the last. Okay? So you have these n minus 1 independent vector fields, and that family is involutive. Okay? So that's a necessary and sufficient condition. Okay? And it's central because it's a necessary and sufficient condition. Even if you look at the proof, you know, it looks, but it's just an impression because it is a necessary and sufficient condition. You get this condition that something has to be equal to 0, and then the theorem becomes, well, if something equals 0, then. Okay, so it looks like you actually played with it. You know, the theorem is not very strong, but actually it is. Okay, it turns out to be exactly a necessary and sufficient condition. Notice that, as we mentioned last time, all of these are vector fields and so on. So every condition is actually dependent on the state. Okay, on where you are. Okay? So it's quite possible that these conditions are not verified everywhere, but just verified in some region, okay? In which case the result will hold in some region. Okay? Remember, we're dealing with nonlinear systems, right? Everything is state dependent. So the conditions are state dependent as well. Okay? All right, so let's see or try to see what these conditions mean. So anybody has an idea about the first condition? Maybe, let me maybe first give you how you would in principle find V. So that gives you a little more of an idea. So we can make this here more specific, okay, by saying, okay, not only is necessary and sufficient condition, but let me give you the recipe to find Z1. Okay. So then Z1 can be found as the solution of the following equation. Here you have a column of 0 and 1, or more generally a non-zero function. Here you have simply the gradient of Z1. Remember, Z1 is a scalar, right? Z is Z1 and so on. Okay. And you have this matrix. Okay. So if the set of vector fields is linearly independent, what can be said about this matrix? It's invertible. Okay? So in other words, because of the first equation, this makes sense in the sense that it gives you delta Z1, gradient Z1. Okay, so let's come back to that in a second. So, interpretation. So without getting into the details of this, just let's look at what would the first condition be if the system was linear. Okay, so suppose we have x dot equal ax plus bu. What is this first condition? Well, we have to compute this set of vectors. Okay, so the first one is b, right? What's the second one? ADFG. All right, so ADFG, so ADFB, right, is FG, which is gradient of G times F, Jacobian of G times F, sorry, minus Jacobian of F times G. So what is this equal to in this linear case? Right? Everybody understands what I'm doing? I'm saying I'm trying to interpret this first equation, and as a very basic way to try to interpret it, I'm just saying, well, what does it look like in the linear case? Okay? So in the linear case, f of x is ax, g of x is b, right? A and b, linear time invariant case. Okay, a and b are constants. So what's ADFB? It's f times b, sorry, b. So it's equal to this. And what is that equal to? So what's the first one? What's Jacobian of b? 0, right? B is constant in an LTI system, right? So Jacobian of b is 0. Okay, so multiplied by f, it's still 0. Okay. What's the Jacobian of f? What's f first? F is ax, right? So what's Jacobian of f? It's just a, okay? So minus ab. So you're going to get minus AB. Any guess of what the next one would be? A square B, right? And so on. And so with a plus or minus sign, okay, minus 1 and minus 1, A and minus 1B. Right? So that's what this first family of vector fields in the linear case looks like. Okay? And we're saying they are linearly independent. In English, or at least what's another word to say this in this case? Saying that B, AB, A square B, A n minus 1B are linearly independent. What? Just saying it's controllable, right? So we know that had to be somewhere, right? This result said, well, whatever the system is, you can do that. It would be suspect, right? So first equation, and you can show this in a more general sense, first condition is just controllability. Okay? So that's not surprising, okay? If we stop there was not this end, it would be an incredibly powerful result, which would say, well, whenever the system is controllable, it's always a sheep in wolf's clothing, okay? But we have the second condition, okay? But the first condition is just controllability. Okay. So, now the second condition. Well, first of all, what does the second condition look like in the linear time invariant case? Because it should apply there too. Well, it's trivially satisfied, right? Because A and B are constant, so whenever you're going to take things like this, you're going to end up with 0. Okay. So trivially satisfied in the linear case, okay. So it's not an extra condition. Now, but let's talk about the nonlinear case, okay? So suppose you believe this, which is the second part of the theorem, which says if these conditions are verified, then gradient of Z1 can be computed as the inverse of this matrix times this vector. All right? Now, this gives you gradient of Z1. How do I get Z1 out of gradient of Z1? Well, I somehow integrate this gradient, right? So, but what does this condition mean? It means that gradient of Z1 is equal to this matrix, the inverse of this matrix, times this constant vector, okay? So it computes a vector, and that vector is gradient of Z1. That's a vector field. Can any vector field be gradient of Z1? No, because not any vector field is a gradient. Okay? So, I'll come back to that in a second. Okay? So, in other words, what the second condition means is that this does make sense. The first condition was saying, well, we can inverse this matrix. The second condition is by inverting this matrix and multiplying by this vector, you get a gradient. Okay? So it's this involutivity condition is really an integrability condition. You do get a gradient. Okay? So that's the story, and we'll come back to in a second why everything is not a gradient if you're not familiar with that. Okay? So these are the necessary and sufficient condition, and the construction, quote, because you still have to solve these PDEs, right? But the construction is this, okay? You compute delta Z1 as the inverse of this matrix using the first equation times this vector, and the second condition guarantees that you end up with something which is indeed a gradient. Okay? Okay? So let me explain a little this gradient story for those of you who are not familiar with it, although, mechanical engineering, something you see all the time in fluid dynamics. Okay, but suppose I have a vector v, which is the gradient of some scalar phi, okay, which phi would be z1, okay. So this vector v is v1, v2, vn. And of course, all of these things are state dependent, okay, so if I could write that v of x is equal to gradient of phi of x. Now, suppose I take the Jacobian of v, okay. This Jacobian of v is simply, as we said, the gradients in line of each of these components, okay. So it's d over dx1 of v1, d over dx2 of v1, and so on, d over dxn of v1. So you have this. And d over dx1 of v1 is d squared phi over dx1 squared. d over dx2 of v1 is d over dx2 of dx1 over phi over dx1. And similarly, d over dx1 of v2 is d over dx1 of dx2 of phi. All right? Now, what do we know about these two terms? D over dx2, d over dx1 of phi on the one hand, d over dx1, d over dx2 of phi on the other hand. They are the same, right? If everything is smooth, right, you have this phi. You differentiate first with respect to x2 and then with respect to x1, or you first with respect to x1 and then with respect to x2, you get the same result. Okay. So what does it say? So this, in other words, this matrix is symmetric, right? These terms are the same. So what does it say that this matrix is symmetric? If we get back to v1 and v2, it says that d over dx2 of v1 minus d over dx1 of v2 is 0, and so on. Right? If you take d over dx2 of v1 minus d over dx1 of v2, you get 0, and it would work with other indices as well. All right? So that's why every vector field is not a gradient, right? Because if we get back to the condition on the vector field, that's a very specific condition on the vector field. Right? If I give you an arbitrary v, in general, it won't be verified. Okay? What is this condition? Suppose you're in dimension 3. How would you write this condition? So d over dx3 v2 minus d over dx2 v3 is 0, and so on, okay? So what is this condition? So everybody sees where we are. We start with a gradient. We say, if this is a gradient, I compute the Jacobian. I get this matrix, and this matrix has to be symmetric. So if something is a gradient, it has to verify these conditions. And you can show it's true the other way around. If it's verified these conditions, it's a gradient. Okay. What are these conditions? What are they called?
Phase of potential.
Okay, so basically, it means that the rotational, the curl of V is 0. Okay? So the curl, if you think of it, these are, how would you compute the curl or the rotational if you want a vector? Those would be the conditions. Okay? d over dx3 v1 and so on minus d over dx1 of v3 equals 0 and so on. Okay, so you would, these conditions are simply saying that the rotational, the curl of the vector field is 0, which is a necessary and sufficient condition for something to be a gradient. Okay. Okay, a gradient is something which is irrotational. Okay. So that's basically what this is about, okay, and again, Frobenius theorem comes in and so on. But you have these two conditions, they are necessary and sufficient conditions, and you have this quote construction through this PDE, okay. This construction assumes two things. One is that this matrix is invertible, that's the first condition. Two, when you compute the corresponding vector as delta z1 equal inverse matrix times this, you do get something which is a gradient. So in other words, that these conditions are verified for the vector you get here. Okay. And so that's the story. And incidentally, the fact that not every vector is a vector field is a gradient, and the more general fact, which is called Helmholtz theorem, that any smooth vector fields can be decomposed as the sum of a gradient and a rotational part, okay, will actually be also the basis of what we'll see later on when we talk about contraction and more general tools for nonlinear systems. And we'll see also that in principle, you can still do quite a lot of things with just the first condition, without the second, okay, but not if you try to transform the system into a linear system, but to transform it into something a little more general. Okay. All right, so questions about that? So this was just trying to explain, why not every vector field is a gradient, because when you take the Jacobian of the vector field, if it's a gradient, it has to be symmetric, and that's a necessary and sufficient condition. And this basically guarantees that the solution delta Z1 will indeed satisfy this property. So, and that's a general theorem, right? A vector field is the gradient of some scalar if and only if curl of V is 0. Okay, questions about that? So we haven't proved, of course, the theorem. I'm just, stating it and interpreting it. Okay. And as you can imagine, this is not very easy to use in general because you have to solve these PDEs and so on, but there's a number of interesting examples, some simple ones discussed in the book and some more general ones and discussed in the literature, where you can use this. In a sense, it's saying somehow your system looks complicated, but it's because you picked the wrong coordinate system. It would look much simpler if you had picked that coordinate system. Okay. All right. Questions about this? Except, of course, we haven't done the proof, but just conceptual questions about this? Yeah.
So what happens if we calculate gradient of Z1 and then we realize it doesn't meet this condition?
No. So if this condition is verified, it will automatically meet this condition. Right? That condition makes sure that this is verified. That condition makes sure that whatever vector is the solution of matrix times this vector is equal to this is a gradient. Okay. But as I said, we'll mention later on in the course what can you do if this condition is not verified and therefore this doesn't work. Okay? This is not a gradient. Okay. All right. Now everybody also sees what I've said at the beginning with robustness. If you start imagining that you have time-varying coefficients in there, or even just unknown things, right? And you start doing all of this, the uncertainty is going to propagate rather fast, okay, for these systems. Okay. But still, conceptually, it's an important thing to understand. All right. Questions? Okay. So now we're going to switch to another direction, which I mentioned last time, which is less general, but and on the other hand is easy, is very easy to play with, and that's something called under the name of backstepping. It's not called this in the book because this term was not usually used then, but it's page 258 and so on. So what's the story? The basic story, there's been lots of variations on this, including lots of variations since the book was written. The story is, okay, so suppose you take a variable and differentiate until you find the input, and you find the input, but much before, or before the nth differentiation. Okay, so you still have z1 to the m is equal to v, and then something else, the leftover dynamics. Okay. Well, we can try to view this positively, say, well, you know, at least now we had the first m equation looked like z1 to the m equal v, right? Very easy, and we have this leftover dynamics. Okay, so we've taken our system. This doesn't work, but it doesn't mean we throw the whole thing away. We can say, well, you know, the first m equations are fine, and now we have to deal with this leftover dynamics. Okay? So that's the basic idea. And it can be done if systems have the right structure, and again, that's discussed in the book, and that's discussed also in literature after that, and is discussed also in the references in the book. So let's give a very simple example. So we are page 260. So suppose we have, first thing is y dot equal v. Okay, so that's, we needed to differentiate our output once to find the input. And the second equation is z double dot plus z dot cube minus z to the fifth plus yz equals 0. Okay. And we're interested in controlling y. Okay, that's what we want. Let's say to 0, just to make it simple. So we have a second order system. This is the entire system. First equation is y dot equal v. So if we're just interested in controlling y, that would be fine. Perhaps it's y dot plus z cube and so on equal v, but we can always rewrite it as y dot equal v. Okay. We can always cancel known terms, right? And then we have this leftover dynamics, z double dot plus z dot cube minus z5 plus yz equals 0. Now, the idea is to say that, well, first of all, does the idea of just designing a controller based on the first equation and forgetting about the rest, does this have any chance to work? Okay, so for instance, has v, suppose we pick v equal minus y, okay, which will certainly make y tend to 0, has this any chance to work? Well, if you think of the 0 dynamics, right? So if you think of the leftover dynamics when y is 0, okay, what is it? It's z double dot plus z dot cube minus z5 equals 0. Okay. So if you make y equals 0 while blissfully forgetting about the rest of the system, it won't work. Right? Because then this equation will clearly be unstable. All right? So the idea, and that's why it was later called backstepping, is to say, let's concentrate first on the hard part. Okay? Actually, that's what you learn when you play an instrument or whatever. You first do the hard things, right? And so let's concentrate first on the hard part. The hard part is really the leftover dynamics. Okay. So let's say, suppose we see for a moment y as the control input to the leftover dynamics. Suppose we see something, for a moment, y is something we can choose to control the leftover dynamics. Okay? What could we choose it to be equal to? So if we could specify y directly, we could choose, for instance, we could choose, for instance, y equal 2z to the fourth, right? Because if we do 2z to the fourth, we get plus 2z to the fifth minus z to the fifth, and so the closed loop dynamic becomes now plus z to the fifth. Right? Suppose we get in this abstract world where we can choose y. If we were able to choose y to be equal to 2z to the 4, right, then it would give us z double dot plus z dot cube plus z5 equals 0, and that would be globally asymptotically stable. Okay? By the way, Lyapunov is coming back here. It's the return of Lyapunov, right? So it would be globally asymptotically stable. Right? And when z tends to 0, then y would tend to 0 as well. So, and that would be fine because that's what we want. Right? So not only this choice would make this leftover dynamic stable, but it's a choice which is compatible with making y tend to 0. Okay, it doesn't mean that it's going to work as such, but at least it's a start, right? If we could do this, then it would stabilize this to 0. And as z would tend to 0, so would y, which was the original thing. So, right. All right. Now, incidentally, what is the Lyapunov function or the Lyapunov function candidate that would show that this dynamics is globally asymptotically stable if we just had this dynamics? Well, it would just be the kinetic energy of this system, okay, plus the potential energy of this system. This V0 is the Lyapunov-like function, the LaSalle function that would show that this system is globally asymptotically stable. Okay? Kinetic plus potential, the usual for x double dot plus b of x dot plus c of x. Okay? Everybody understands this? Okay, so this is the Lyapunov function that would show that the system is stable. Okay, so where are we? We've just said, well, if somehow we can make y equal to z square, we would get this. To z4, we would get this. And the fact that this works would guarantee, would be compatible with the fact that y tends to 0. Okay. It's compatible, but it still doesn't show that it works. Okay, so to show that it works, we have to build a Lyapunov function for the entire system. Okay. So the idea is actually, if you think of it, it's exactly the same idea as an adaptive control. Okay. So we're going to pick as a Lyapunov function, or Lyapunov-like function, to try to describe the entire system. This V0, which assumes that this is exactly true, plus the equivalent of A tilde transpose P inverse A tilde, right, in adaptive control, which is 1/2 of y minus 2z4 squared. So it's exactly the equivalent of A tilde transpose A tilde, if you want. All right? So we have V0, which is the term which we would have. This is just an analogy, okay? You don't have to think about adaptive control, but it turns out to be exactly the same. Right? So this is the term we would have if y was equal to 2z squared. Right? So if we just had this dynamics. And we add to z4, sorry, and we add how far is it from 2z4 square. Okay? So if we compute v dot, what are we going to get? Well, we won't do all the algebra in detail, but what do we expect to get? Okay. So the first term we'll get is minus z dot to the 4, okay, which would be the damping term. Okay, so in other words, if we just had this and we computed v0 dot, we would, there's not an x, of course, it's a z here. Okay. If we computed v0 dot, we would have simply the damping term minus z dot 4. Okay. So that's, but of course, we have an extra term, and if we compute this extra term, we'll find that it's equal to zz dot times a term which is not surprisingly proportional to y minus 2z4. Okay, so that's v dot 0. V dot 0 here, the derivative of this, right, is equal to what it would be if y was exactly equal to 2z4 plus a term which is proportional to y minus 2z4. Same thing as we say, you know, it's what the dynamics would be if a hat was equal to a plus a term proportional to a tilde. Right? And then we have the derivative of the second term. So the derivative of the second term gives us, well, whatever the algebra says, okay? So, which is, okay, so we can do it right. It's going to be 2 times this term, right? 2z4 times the derivative of this term. And there's no 2 because it was 1/2. Minus 2z to the 4. Okay. So if you regroup everything, you'll find, let's get the algebra here, minus z dot to the 4 as usual, okay, plus y minus 2z4, which factors out here and here. And then v minus 8z cube z dot minus zz dot. Okay, so this is just by doing this algebra. Okay, so now we have this minus z dot to the 4, which is nice and negative, and then we have this term, which is y minus 2z4 times something, but of course v is what we can choose. Okay, So now what we would like, right, is this term to be choose V so that this term V minus and so on, right, is simply y minus 2z4. Right, because then we get a square. Okay? Which means, of course, pick V to be equal to minus y plus 2z4, okay, plus 8 z cube z dot plus z dot. Okay? So if we choose V such that this is verified, okay, then we get this particular choice for this small v, okay? And then, of course, then v dot by construction is equal to minus z dot 4, okay, minus y minus 2z4 squared. Okay? And then, of course, we can finish the proof with the invariant set theorem, because now we have this nice set of two negative terms. Okay? Okay. So what was done here, right? We said, let's start by looking at the hard part, which is this leftover dynamics. Let's say that if y was equal to 2z4, then this leftover dynamics would be globally asymptotically stable. If y was. And now let's define a Lyapunov function for the entire system as the sum of V0, which is the Lyapunov function that shows that this ideal leftover dynamics would be globally asymptotically stable, plus an extra term, which is how far y is from 2z4, because we still have to show the overall stability. And so when we differentiate this, we find that the derivative of V0 is this nice negative term plus something which is proportional to how far y is minus from 2z4. And that term is going to be cancelled by the derivative of this second term, exactly as in adaptive control. The a tilde term is cancelled by the adaptation law. Okay? So what plays the role of the adaptation law here is the choice of v. Okay? So that's the basic idea. And one aspect of that idea, which is particularly nice, is that it can be applied recursively. Not surprisingly, in a sense. Okay, so in a sense, it's saying, okay, I have this leftover dynamics, I control it, and then I go one step up. Okay, and now you can do this for more complicated systems. So we won't do it in detail, but let me explain at least the idea. So first of all, everybody understands this, right? Okay. So suppose that we now have this system, okay? So incidentally, you have lots of exercises at the end of that chapter, which were just chosen to be scary, but which they are not, you know, it's just, so this is similar to that. So suppose we have this system we want to control x to 0. What could we do? Well, first of all, of course, this part is a joke, right? We can replace this whole thing by equal v, right? It's, we can just call it v, right? So that's not a big deal. Okay. So, what about the rest? Well, let me give you a hint. This example was chosen with this one in mind. Okay. Well, suppose we consider for a moment x as the control input of these last two equations. Right? What would we like to choose it to equal to? So it's exactly the same story. Okay? If we could specify x directly, we could choose. What would we choose? Well, we would just choose this, right? So we would choose x equal minus y plus 2z4 plus 8z cube z dot plus zz dot, plus, of course, this extra term which was just added for fun, okay? So plus y cube z squared. Right? The idea being that this term and that term are the same. Right? So if we could specify x directly, we could choose this, right? That's what we've just shown. Right? Hence this backstepping idea, right? We've just shown that this choice of control law, right, with canceling this extra term, it's exactly the same structure up there, y dot equal v, right? We could choose this to take care of this part. Is that clear? So what are we going to do now? Well, we're going to pick v to be the same function I have up there. Okay, so maybe I could call this v1. Okay, so I'm going to pick v equal v1, which is the v I just had before. Okay, plus, well, 1/2 of x minus this whole thing. Okay, so I can call this, if you want, x0. Right? Where v1, again, is just my previous v, okay? This v here. All right? So v1 is the one that shows that this x, if it was viewed as a control input, would stabilize this leftover dynamics. And then I do exactly the same thing, right? I go one step up. All right? And by going up one step up, I get v dot is equal to, well, I'm going to get minus z dot to the 4, exactly as before, minus y minus 2z to the 4 square, exactly as before, okay? Plus a term in x minus x0 times v plus something. You have the algebra in the book. I don't think it's worth writing every single term. So, and then of course, we're going to choose v so that this equals minus x0. So that this whole thing becomes minus x0 squared. Okay? And so it's the same story, right? It just says you have a system like this, okay? So first do the obvious simplifications, get rid of the obvious terms, okay? Then solve first the last two lines. It so happened that we had done it before, okay? And then, based on that solution, solve the entire system. Okay? And this notion of backstepping, which requires, of course, which relies on a particular structure of the system, right? But that's what you get. And it says, start with the most difficult thing and then back up. And of course, if we just started with this, okay, we would in a sense say, this is the most remote dynamics, right? Because you have u that controls x, x that controls y, and y that controls z. Okay, so we start with the most remote dynamics, right? We back up one step. That's what we had done just before. And then once we have that, we back up one step. Okay, which requires this kind of hierarchical structure, but it's the basic idea. Notice also, we didn't have this problem before. Here, notice there's going to be an x0 dot coming up, right, in this algebra. But we have x0, we have the dynamics, we assume everything is exactly known, so x0 dot can be computed formally, right? X0 dot is simply computed formally from the dynamics. Okay. All right, so 2 point of views, right? This general, precise, necessary and sufficient theorem with its integrability conditions in the form of PDEs. This, which applies to, which is less general but relatively simple, which basically uses Lyapunov on a simplified system, simplified because you've differentiated until you found the output. So here, in both of these examples, the simplified system was something dot equal v, but it could be something to the 7th power equal v. Okay, that's still the simplified system. Okay, and then the rest. And then you basically build Lyapunov-like function recursively, starting from the most remote part of the leftover dynamics and slowly backing up. Right? And this is also using Lyapunov tools, so it's also to some extent more amenable to problems of parameter variations and things like that, because you could be able to mix, on the effect of unknown parameters and so on to some extent in these kinds of computations. All right, so that's the general story, if you want, that we'll cover here about feedback linearization. And so next time we'll start looking at a new set of tools, which by the way, I've alluded to several times in the course, saying, well, we will show later in the course that and so on. So, well, later is now. Okay. So that's a new set of tools. And at some point also, it won't at all be the central part of that. But at some point also, we'll see if you have systems like this, what can you do precisely if you only have the first condition verified, in other words, just the controllability condition, okay? And we'll see that in a sense you can do quite a bit if you don't try to force the system to look linear, okay? But just to look like a more gentle nonlinear system. Okay? So that's what we'll start seeing next time.